shall have a look at the one more category of activation functions, which are called as sigmoidal functions. Now previously we have seen different functions, okay, and I will concentrate on two types. We have seen a unit step function, and unit step function will be varying between two values 0 and 1. Then we have seen another function that is not a unit step function, but we call it as a signum function, and these two levels are nothing but 1 and minus 1. So 1 and minus 1, these are two levels which are there. If at all, these are the two activation functions which are binary functions, or which describe the discrete neuron. So why it is discrete? Because it has got only two levels, 0, here the levels are 0 and 1, and here the level is minus 1 and 1. These are the only two levels which are present. Now what happens is that if at all you notice here at this particular point, there is a discontinuity. Similarly here there is a discontinuity when it switches between minus 1 to 1. So usually this point is 0 when it is equal to 0. So this is defined as a threshold. But what happens is that at this, if at all this is f of net, that is the activation function, then because it is not continuous, if at all you would have studied mathematics that if at all a function is not continuous, then it is not differentiable as well. You cannot find a derivative of that particular function. So when you cannot find a derivative, it is not possible to find f dash of net or f net dash. You cannot find the derivative. So we have to move on to other functions. Now we also have seen what is the meaning of a ramp function. We have seen a ramp function, and in the ramp function we have tried to remove this discontinuity, and it is made somewhat like this. But still, although it is a continuous function, but yet the function is not differentiable at these 2 points. Although it is continuous at these 2 points, but what happens is that there is an ambiguity with respect to the derivative at these particular points, because it is like a corner. So that is the reason at these 2 points it will be not differentiable. So again there is a unipolar ramp function, a bipolar ramp function, depending upon whether this is 0 and 1. If these two levels are 0 and 1, then it is unipolar ramp. If at all these levels are 1 and minus 1, then it will be a bipolar ramp. So again, the ramp function has got the problem that it is not differentiable. Hence we switch on to something, we require some function in neural networks which is continuous and differentiable. So a function which is continuous as well as differentiable. So we went on from this, we went on to something like this, and finally we are coming to something like this, and this is what is sigmoidal function or S-shaped function. So if at all you see this is a step function, this is a ramp function, and what we will be having a look at it now is a sigmoidal function or S-shaped function. Because the shape is S, of it's of the shape of the alphabet S, and that is the reason it is called as an S-shaped function. Now, looking at this particular graph, is it a continuous graph or it is discontinuous? Does it have some discontinuity like this or like these points? No. So because it is a continuous function, the function will be differentiable everywhere, and that is the reason it is possible to find f dash net, and that is what we call as the sigmoidal function. Is that clear? So if at all we see what is a sigmoidal function, you can look at this. What it is said is that the function is continuous and differentiable everywhere. So we have seen from the graph that the function is continuous and differentiable everywhere. So you can see this particular graph, the function is continuous everywhere. Then it is rotationally symmetric about some point net is equal to c. So this particular point, I write it as net is equal to C, and I am not much interested in these particular values. Say, I'm not interested in these particular values. So I'm more interested in the shape of this graph. So this is one particular point. This is say point B, and this is say point A. And what is this? This is the point net. So this side you have net, and this side you have f of net. Okay? So if you want, you can, if at all you consider it like this, then it may be a unipolar. So looking at this particular graph, I can have both the ways. That is, these two levels I can, the S-shaped function can be somewhat like this. Is it a bipolar sigmoidal function or it is a unipolar? This obviously is a bipolar because it is both in the first quadrant and as well as in the third quadrant. Similarly, we can have a unipolar sigmoidal function, and the unipolar sigmoidal function will be how? It will be like this. It will be somewhat like this. So this is the S which will be there. So the unipolar function, unipolar sigmoidal function. Now both these functions are continuous functions. If at all you see, both the functions are continuous function and they are used to define a continuous neuron. So previously we have seen discrete neuron. Okay, the previous functions, the step functions, were used to define a discrete neuron, but sigmoidal functions are used to define a continuous neuron. So what you can see is that the function is rotationally symmetric about some point. So the function is symmetric rotationally, meaning what? If at all I rotate this particular function, then also it will be symmetric. So how will you rotate is basically, you can imagine it that there is one more axis and if at all it's rotated. So I can convert this particular function into a three-dimensional function, and even if at all you do that, it will be symmetric. So I cannot, as of now you all may not be able to visualize that, but in the practicals you all can plot and see how it would look like. Now then again, this function is asymptotically approaches its saturation values. Which are saturation values? This is the saturation value, the higher saturation value. This is the lower saturation value, A. So it will be approaching a particular maximum as net goes on increasing, and it will approach a minimum as net goes on decreasing. Is that clear? So now we shall have a look at so what does it mean when I mean to say asymptotically it increases or decreases? What I can define for this particular function is that from this graph as limit of, so if at all I find the limit, so as limit of net tends to infinity, f of net, what it will be? As net goes on increasing, what is the value of the function f of net? The function approaches b. And as limit of net tends to minus infinity, f of net will be what? It approaches this side, that is it approaches A. So this is a sigmoidal function. Now we will be going into the details of another function, that is sigmoidal function for unipolar continuous neurons. So we shall have a look at this particular function, and then we shall be going and having a look at the bipolar continuous sigmoidal function. Is that clear? So next, so the function is also called as logistic function. So it is a sigmoidal function for unipolar continuous neuron. So what is the equation of this particular function? We shall write the equation of this particular function. F of net equals 1 upon 1 plus exponential of minus lambda net. Now lambda is a constant which is used, will be changing the slope of this particular function. So, if at all I draw this particular function, how will I get this particular function? The function will be somewhat like this. So this is the S-shaped function for this equation. Now what is this value here? The lowest value which the function takes is 0 and the maximum value which the function takes is 1. So this value will become say 0.5 and here obviously this value is 0. So this is nothing but f of net. So this is S-shaped function and as you can see the function is continuous everywhere. Now the slope of this particular function varies with the value of lambda. So the slope of the function will vary with the value of lambda. So if at all lambda is equal to 1 then maybe we get this particular shape. If at all lambda is equal to 2 we may get some other shape as in the slope will change. So it would be somewhat like this. If at all I will draw say 3 different colors. So if at all somewhat like this. So I have drawn the function, S-shaped function, logistic function for 3 different values of lambda. So in the first case maybe the value of lambda is say this case, say lambda is equal to 1. Then in the second case I am just giving the value is lambda is equal to 1.5 and in the third case, that is the green case, say the value of lambda is 2. So as the value of lambda goes on increasing, the slope goes on, the slope becomes steeper and steeper. And when the value of lambda is less, then the slope is it is a very gradual slope. You can say like this, somewhat like this. Okay, so this is what maybe this one can consider as lambda is equal to 0.1 and the one which I drawn previously, this one may be considered as this one. So lambda is equal to 0.5 or something like that. So what at this point you will need to know is that as the value of lambda changes or increases rather, the slope becomes steeper. Okay? Now we shall just go in and see whether the function is continuous. We have already seen, but now we shall check whether the function is differentiable. If the function is differentiable, what will be the derivative of this particular function? So before that, what is the range of this function? Range of this function is the function lies between 0 and 1. So the smallest value is 0, the maximum value is 1. Now we shall calculate f net dash. So we know what is f net. So we'll calculate the derivative. What is f net dash? Okay, so what is f net dash? This whole thing raised to the power 2 multiplied by the derivative of the inside part. Multiplied by the derivative of the inside part. What is the derivative of the inside part? The derivative of this particular part is exponential minus lambda net. And what is the derivative of this inside part? The derivative, okay, first whenever here this minus 1 should come, because what is this function? This function is nothing but 1 plus exponential minus lambda net raised to minus 1. So when you take the derivative of this, minus 1 should come out upon this term raised to the power 2. So this is the derivative. The derivative of inside part is exponential of minus lambda net, and then the derivative of this inside part is minus lambda. So if at all you put all these terms together, what you get is lambda exponential of minus lambda net upon 1 plus exponential of minus lambda net the whole square. So this is f net dash. Okay, this is f net dash. So now there is sometimes a question which is asked to prove that f net dash is equal to something. So we shall do that part also. So first we have calculated derivative which indicates to us that the function is continuous, hence it is differentiable, hence we can find the derivative of the function. We have to prove that f dash of net is equal to lambda f of net into 1 minus f of net. Now we already know what is f dash of net. So first we shall write the equation of f dash of net, and then we shall find the right hand side. So what is f of net? F dash, so f of net is this 1 upon 1 plus exponential of minus lambda net. Now we want this term we have got, now we want this term. So what we shall find is 1 minus f of net. What is 1 minus f of net? 1 minus f of net will be 1 minus 1 plus exponential of minus lambda net. So if at all we do this, it will be 1 plus exponential minus lambda net minus 1 upon 1 plus exponential minus lambda net. So this one and this one will get cancelled, and we are remaining with exponential of minus lambda net 1 plus exponential of minus lambda net. So I have found out this. Now next step is to find out f dash of net. So when we find out f dash of net, we already know, we have done it. If it is asked in the exam, you have to actually do that previous step. Where we have done it here? We have already done it here. So this is f dash of net. So I will directly write the answer because we have already done it. That is lambda exponential of minus lambda net 1 plus exponential of minus lambda net the whole square. Fine. So we have already got this. Yeah. So now only thing that is left is now to equate. Now if at all you multiply this term, with this term, what you will get? You will get this into this. In the numerator, what you will get is, so this is say this is your left hand side, and what is your right hand side? Right hand side will be, if at all you multiply lambda, so I take green color, lambda f net into 1 minus f net, what will you get is 1 into this term, and obviously there is a lambda term which you have multiplied, lambda into f of net. This is f of net, and 1 minus f of net is nothing but exponential of minus lambda net and this. Fine. So when you multiply this and this, you finally get nothing but the same thing. Square. And what is this? This is nothing but right hand side. So From this you can come to know that LHS is equal to RHS, and that is the reason it is proved. So finally we have been able to prove this particular statement. So now next, what is the advantage of this particular type of function? Sigmoidal function for unipolar. Coming back to this sigmoidal function, okay, this is this one itself. So coming back to this particular function, we shall just have some points, write some points with respect to this particular function. And now, what are these points? This particular model is useful where we have predict the output. So we have to predict the output of a particular function, then it is useful. Also, the function is differentiable. The function is differentiable, and hence, because it is differentiable, what happens is that the function is differentiable and it is monotonic function. So the advantages of this particular thing is that the function is differentiable and it is monotonic. Now what is the meaning of monotonic function? Monotonic function means a continuously increasing function. So if at all I write something like this and then like this and like this is a non-monotonic function, because as your net goes on increasing, your f of net is not increasing, it is increasing, decreasing, increasing, decreasing. So it is a non-monotonic function. But if at all you get this particular function, it is an S-shaped function, it always goes on increasing, so it is a monotonic function. But if at all we find the derivative of this particular function, we have already found the derivative here. This particular function, the derivative is although, is it a continuous function? The derivative is continuous. That is, the derivative of this particular function is continuous, that is dash net, but it is not monotonic. Okay, if at all you will be using these functions in MATLAB, then you can first plot f of net and then you can plot the derivative of this particular function and check the shape whether it is monotonic function or not. So it is not a monotonic function. Why? Okay, looking at this particular term only, you can make out that there are, see this is in the denominator and this is an exponential function in the numerator and in the denominator only. So because of that, we come to know that it is inversely proportional to the exponential of net. So it is going on increasing. But here, in the numerator, it is directly proportional. In the denominator, it is inversely proportional. So it is not a continuously increasing or decreasing function. It is a complex relationship between net and f of net. So we'll go to the next one, that is the second type of function, that is a sigmoidal function for bipolar continuous neuron. Okay, so we have seen unipolar continuous function. Now we see bipolar continuous function. So the only thing is that the signal should be in above the net axis as well as below the net axis. It is not only above the net axis. So this is also called as 10H function or hyperbolic 10 function. Remember that the previous one was called as logistic function. That is, this one is logistic function, unipolar sigmoidal function. So now this particular function is only on top. So if at all we want to extend the function, then there is a technique which is used from mathematics. So how we get the equation for bipolar sigmoid? You take the unipolar sigmoid. So bipolar sigmoid, how you get it from the unipolar sigmoid is that you multiply this function by 2i's minus 1 and you shift it back. So if at all this is a technique from signals and systems, You are scaling the function the factor 2 and then you are getting it down, that is you're shifting the signal down by -1 so that you get the desired shape. So if at all you do that, what would happen to your signal is somewhat like this. You all can do it along with me. So now what happens is that if at all you just simplify the mathematics and you will get this. So the equation is of this form. Okay, please don't get confused. All this time I am writing lambda is one term, net is another term. These are two terms. Don't write it as one term. Okay, so final equation of our function g of net is nothing but, now this is nothing but your 10 hyperbolic function. If at all you remember from your mathematics, it is of the form of 10 hyperbolic function. So what is the range of this particular function? How would you get this particular function? If at all I draw a function, it would be like this. The function would be somewhat like this. So what is the lower value? The lower value is -1 and the higher value is +1. So again, okay, so this is the shape of the function. So it is a bipolar continuous function because it is there on top as well as below. So it is a bipolar continuous activation function. Why it is continuous? Because it is continuous function, it is differentiable also. Now, what is the range? The range lies between -1 and +1. The range of this function is between -1 and +1. And if at all you want, with the varying values of lambda, you can plot the graph again. Say if at all this is, say, lambda is equal to 1.5, then with another different values you can just plot somewhat like this. And one more I can plot. So this we say is lambda is equal to 1. This one maybe lambda is equal to 1.5. I think it's better to write in that particular color itself. And lambda is equal to 2. So again, as value of lambda increases, the slope becomes steeper and steeper. So now what I want you all to do is that we shall just go with the characteristics of this particular function, and after that you have to derive f dash net, and I will give you, you have to equate it to what? So this particular part I will not be doing, but I want you all to do, because one derivation of Unipolar sigmoidal function I have done, one derivation you will be doing, and similar approach it is. If it all you do not get, that you ask me. Now before that, here what happens is that, what are the advantages of this particular function is that the negative inputs are mapped to a negative output. They are strongly mapped to the negative output. Similarly, the zero input is mapped near 0, and the positive inputs are mapped strongly to positive outputs. So you can write this and keep, I am just saying it, I am not writing it, but you can write it. Negative inputs are mapped strongly to negative output, zero input is mapped near to 0, and positive inputs are mapped strongly to the positive output. Then the next point is function is differentiable and it is monotonic. As you can see, function is differentiable. Why it is differentiable? Because it is continuous. So because it is continuous, it is differentiable, and because it is differentiable, not because, because it is differentiable, you can find the derivative. Besides that, the function is monotonic, but the derivative of the function will not be monotonic. You can find the derivative of the function. The derivative of function is not monotonic. Similar to the previous one, derivative is not monotonic. Now this particular function, not only this but 10 hyperbolic function and the logistic function, both are used in feed-forward neural networks. So they have a very important role to play. Now students, this is what you have to prove. You are given the bipolar continuous sigmoidal function, which is this much, and you have to find the derivative g dash of nat and show how it equals to the activation function. So this is what you have to prove. Next function is Gaussian activation function. You all would have studied previously Gaussian functions in different subjects. So now Gaussian function is also called, it is a bell-shaped curve, and it is also called as radial basis function. So the equation is given of this in this particular form. F of net is equal to 1 upon root 2 pi sigma into exponential of minus half, and into it is net minus mu upon sigma the whole square. Now if at all you know what is sigma, mu, it is mean, and sigma is nothing but the standard deviation. So standard deviation. So if at all we plot the graph, how would that graph be? It would be like this. So this is net and f of net, and as everybody knows the shape of a Gaussian function, this Gaussian function takes this particular shape. Okay, so this is the function. Now what will be the effect of changing this mu and sigma? Now what is mu? Mu is nothing but this particular point, and something here I can show as sigma. It is a, if at all we change mu and sigma, what would just happen is that I could just show you. This is a graph with mu is equal to 0. So here is mu, the mean value is equal to 0. If at all I draw a graph with say mu is equal to 1, then how it would be the here? So the graph would be shifted somewhat like this. So the mean value, which is the maximum value of the Gaussian function, will be 1. So if at all I want mu is equal to 2, or mu is equal to 5, or mu is equal to 3, then the Gaussian function would be shifted somewhat like this. This is mu is equal to 3. Similarly, it could be shifted on the other side also. So this is the effect of changing this particular term. If at all you change this particular mu, now here, if mu is equal to 0, here nothing will be there, it will be net upon sigma. So by changing the value of mu, you can shift the Gaussian shaped curve. Now what would be happening if at all I change sigma? So if at all I change sigma, this is one particular graph of mine. If at all you decrease the value of sigma, what I would get is that I would get a very narrow curve. If at all I increase the value of sigma, then I will get a very broad curve. So this sigma value is less, sigma 1 is, so this is say sigma 1. So sigma 1 is less than sigma 2 is less than sigma 3. So if at all the standard deviation is more than the, if at all it means that the deviation is more. This particular value is more. So this is your sigma 3. So the standard deviation is more, that it will be a broader shape Gaussian curve, bell curve. Is that clear? Coming back to this, it is a continuous function and it asymptotically approaches to 0. So both the previous cases, one side it would approach to 1, other side it would approach to 0. Or one side it would approach to plus 1, other side it would approach to minus 1. So here both the side it approaches to 0. And it has got a single maximum value, that is at mu. Is that clear? So this is what is Gaussian activation function. It is used nowadays. Earlier it was not much used in artificial neural networks, but yes, now there is something called as RBF, radial basis function neural networks. So for RBF nets, etc., this particular activation function is very useful. Okay, today we shall just have a brief idea about how the activation functions are classified into two broad classes. One is called as hard limiting activation functions and the other class is called as soft limiting activation functions. So hard limiting activation functions are used to model a discrete neuron and the outputs will be either 0 or 1 for unipolar case and it will be -1 and 1 for a bipolar case. Whereas soft limiting activation functions are used to model a continuous neuron and the outputs will take the range between 0 and 1 for unipolar case and it will take the range between -1 and +1 for bipolar case. So now the examples of soft limiting activation functions, as you have already studied, are sigmoidal functions, which are logistic function and hyperbolic tangent functions, and the examples of hard limiting activation functions are binary functions such as unit step and signum function. So we have the unipolar function and the bipolar function, which is, this is the unipolar function, that is the hard limiting function, and this is the bipolar hard limiting function. So this is your unit step function. So this is unit step function and this is your signum function. So similarly, if at all you see here, these are sigmoidal functions which are there. So this is unipolar sigmoidal function is your logistic function and this is your hyperbolic function. So if at all you see here, the decision boundary which is there is a very sharp decision boundary here. Here also the decision boundary is very sharp and that is the reason it is called as a hard limiting function. So it is a thresholding, sort of a thresholding function because the decision boundary is very sharp. Whereas you can see here there is no sharp decision boundary here. It is a very smooth curve and therefore it is called as a soft limiting activation functions. Here also there is a very smooth curve and there is no sharp cutoff as such which takes place. It is not a threshold function. So it is a thresholding function. Is that clear? So now we move on to the next part, that is how it is shown in terms of a model. So these are the models which are shown for both of these particular hard limiting as well as soft limiting functions. So if at all you can see here, in case the first part is the same, there is a summing node which is shown and the second unit is a threshold logic unit function. So as of now it is shown as a bipolar. So whenever usually this particular model TLU is shown, it is understood that it is a bipolar, and in this case a continuous neuron is modeled in this particular way. So if at all it is shown in this particular way, it means it is a continuous neuron. So sometimes in place of showing you this full thing, it may be just shown like this. So that time it may be a discrete neuron. So here, whenever it is shown in this particular form, that is a triangular form, it is always a soft limiting neuron. Now this soft limiting neuron, again if you see at the equation, it is equation of a bipolar activation function, bipolar continuous activation function. Is that clear? So now, a hard limiting neuron is called as binary perceptron, and soft limiting neuron is called as a continuous perceptron. So this, what is shown in this particular figure, it is a binary perceptron, and what is shown here is a continuous perceptron. Now here, as you have seen on the previous slide, the decision boundary is sharp, and here the decision boundary is smooth.